Hello, my name is Shalini. I'm from Redmond, Washington. My mentor's name is Hosni, and my Polygence project is on parameter estimations using gravitational waves. I chose to research this topic because I'm fascinated by space, and I think it's really cool that objects such as black holes produce gravitational waves that we can detect and use to learn about the events that created them. Black holes and gravitational waves are both mysterious phenomena with huge scope of discovery still, which makes this an important area to research. So, what are gravitational waves? They are these ripples in the gravitational field that travel at the speed of light. They were first predicted by Einstein's general theory of relativity, where he stated that when an object with a really high mass accelerates, it distorts space-time and causes gravitational waves to ripple out from the source. The most commonly detected sources of gravitational waves in our universe are black hole mergers and neutron star mergers. Say you were to throw a pebble into a pond of water. You would see ripples come out from the source. Based on how big these ripples are, you could probably tell how big of a pebble you threw in. Gravitational waves are like those ripples. They carry crucial information about the properties of the event that they're caused by. These properties are known as event parameters. You can analyze gravitational waves to estimate the values of these event parameters. But how do you analyze waves that have no physical form? The answer is, you use these highly sensitive instruments known as interferometers to detect them. There are two interferometers in the US, where they are referred to as LIGO instead, which stands for Laser Interferometer Gravitational Wave Observatory. There is one in Hanford, Washington, and another in Livingston, Louisiana. They are these L-shaped structures with super long arms, 4 kilometers long. How do they work? LIGO uses lasers, as the full name suggests. A mirror at the intersection of its two arms splits a laser into two beams, sending one down each arm. The beams reflect back and forth 300 times before recombining. If a gravitational wave passes through, it causes a tiny change in the arm's length, a change that is so small it is smaller than the width of an atom, and this change alters the travel time of the laser beams. So when they recombine, this produces an interference pattern, which LIGO measures to detect the stretching and squeezing of space that was caused by the passing gravitational wave. This interference pattern can be plotted on a graph. The graphs here show the strain, the tiny stretching and squeezing of space, as a function of time. These graphs show the gravitational waves caused by the event GW150914, which is a merger of two black holes. They show peaks corresponding to the precise time of the merger when the gravitational wave signal was the strongest. Here's a brief explanation on how neutron stars and black holes form. When a star much more massive than the Sun runs out of nuclear fuel in its core, it collapses. If the collapsing star's core has a mass of approximately 1 to 3 solar masses, it becomes a neutron star, while more massive cores collapse into black holes. In my Polygence project, I'm using LIGO's gravitational wave data from the black hole merger event GW150914, which I mentioned earlier, to figure out properties of the merger, which includes the individual masses of the black holes before they merged, their trip mass, which is a combined mass of the black holes that also determines the frequency of the gravitational waves as they rose over time, the individual black hole mass ratios, the distance to the merger event, and the time of the event. The goal of this project is to essentially understand what gravitational waves can tell us about the cosmic events that created them, and also how we can use these waves to figure out the properties of those events. So, how do we do this? Well, we use this thing called the Bayes theorem. It's a mathematical framework that updates the prior, which is any existing knowledge or beliefs that we have about our event parameters, based on the data that we observe, which is the strain data from LIGO in our case. The updated belief refers to the posterior. The Bayesian inference is a method that implements Bayes' theorem to make parameter estimations. Here's an example to better explain it. Imagine you see a cardboard box on the street next to a bunch of empty cardboard boxes. You would probably assume that this box is empty as well. This is your prior. But then what if all of a sudden you hear a meow that seems to be coming from the box? This is your observed data. Based on the data, it's probably safe for you to assume that the box is in fact not empty and that there is a cat inside the cardboard box. This is your posterior. This simple example shows us how our assumptions change once we have new information, which is exactly what we do when we are trying to estimate parameter values. To estimate our parameter values, we use the MCMC method. It's a Bayesian statistical method in which each parameter is given a range of possible values. Values from this range are sampled for using Python packages like Bilby to find the most probable one. The results can be visualized using corner plots like the one in this image, which shows the Gaussian posterior distributions of the parameters I sampled. And here are the results from my sampling compared to the ones from the LIGO catalog. I sampled for chirp mass, mass ratio, distance to the source, and event time. And then I used chirp mass and mass ratio to calculate the individual black hole masses. My estimates aren't perfectly precise due to limited computational power. Sampling for only 4 parameters, which is a lot fewer than the total number, can reduce the accuracy of your results, and sampling for more was impractical because this computation on its own took me 8 hours. But despite this, my results are reasonably close to the actual values, and they're good enough to achieve my project goals. I believe a good area for future research is LISA. It's a space-based interferometer made up of 3 spacecraft that are 2.5 million kilometers apart from each other. Its lasers will travel about 2,000 times farther than those in LIGO, allowing it to detect much weaker gravitational waves, potentially from supermassive black holes, which are the black holes in the center of our galaxies, and even cosmic microwave background. Modeling these expected signals and analyzing their implications could give us a deeper insight into the early universe and how it formed. And this shows us just how much more there is for us to explore in gravitational wave research. And that's the end of my presentation.